In this video and the two that follow, I'm going to solve a few mechanics problems using Lagrangian mechanics. Now, we've already gone over a couple of the advantages of using Lagrangian mechanics, the most important one being that it doesn't matter what coordinate system you're working with. The procedure for solving the problems is the same. The other advantage is that you can ignore constraint forces. Now, the first one is the most important one, because what it means is that solving mechanics problems, at least those classes of mechanics problems that are amenable to Lagrangian mechanics, becomes almost a mechanistic exercise. Not completely, but you can formalize it in a way that makes the procedure repeatable, and you can come up with a set of rules that you can repeat every time that you solve a mechanics problem. So I've summarized here what I think is a good procedure. So the first thing is that you ensure that all the forces that you're working with, except for the constraint forces, but all the non-constraint forces, have a potential energy associated with them. If that's not the case, then you can't use Lagrangian mechanics, at least not on the form that we have discussed it. Then you should choose a set of generalized coordinates that go well with the constraints that you are going to choose. And once you've done that, you can write down the potential and kinetic energies in inertial coordinates. That could be the generalized coordinates, but you have to make sure, though, that in that case, the generalized coordinates themselves are actually inertial. If not, you can just write down the potential and kinetic energies in regular Cartesian coordinates and change variables later. It's up to you which you prefer, but that procedure tends to be safer because you don't run the risk of falling into the trap of writing down these in a non-inertial frame, in which case you will get the wrong result. Then you write down the mathematical constraints, making sure that they're holonomic, but everything we encounter in this course will be holonomic. Then, if you didn't write down the kinetic and potential energy already in your generalized coordinates, you make the change here, and then you apply the constraints, which should reduce the number of variables you have to work with. You write down the corresponding Lagrange equations, and then you solve. Okay, that's the method we're going to use. And I'm going to keep this list here, at least in the beginning, so that it becomes clear what we're doing. So the first example that we're going to treat is that of the Atwood machine. Which looks like this, right? A couple of masses attached to this wheel here. To make things a little less complicated at this initial problem, I'm going to assume that this wheel here is massless and frictionless, and the string is also massless. The only thing that have mass are these two weights here. Now, this problem you can, of course, very easily solve using regular Newton's second law approach that you have used in intro mechanics, and we also solved it earlier using an energy approach. So now we're going to solve it again, but using Lagrangian mechanics. So the first thing we have to do here is ensure that non-constraint forces have a potential associated with them. Well, the constraint forces are the forces here in the string. We don't actually have to worry about that. We can write down a potential associated with that, as we have seen, but that only means we get more variables than we want to work with. So the non-constraint forces that we have, the only one is force of gravity, and there's a gravitational potential associated with it, so that's fine. Then we should choose generalized coordinates. And to do that, I'm going to say that, well, let's see, how many particles do we have that move? We have two objects that move, and the motion is only in the vertical direction. Okay, so we have two objects, motion only vertical. So that means that we need two generalized coordinates. We're going to use the same generalized coordinates that we used when we solved this earlier, using energy approach. So I'm going to take them to be these two values here. So I'm going to call the distance from this midline down to the first mass x, and I'm going to call the distance on this side y. Those are my generalized coordinates. Now, y and x are not perpendicular to one another, but nothing says they have to be. That's just a convention. All right. Now we should write down the kinetic and potential energy in terms of inertial coordinates. X and y are inertial because this line here does not accelerate. So we can do this relatively easily. Kinetic energy first. It's going to just be 1/2 m1 x dot squared. And then the second mass here. That's the kinetic energy. Then we have the potential energy. That's minus m1 gx minus m2 gy. All right. And the minus signs are because x and y are both in the downwards direction. Okay, now we need to apply a constraint. That's the next step. So the constraint here is, it's the constraint of a stiff wire. It does not stretch. So I would call this the no stretch condition. We've done this in class already. So this means we can say that x plus y plus pi r, that's the distance across the top half of this wheel here, that has to equal to some L that we're working with. Okay, that's the length of the wire. What this really means is that we can write y as minus x plus some constant. That constant happens to be L minus pi r, but it doesn't matter. It's not going to, we're not going to need to know what that constant is, so I'll just keep it as c. Then we have y dot equals minus x dot. And that's really, those are really the constraints that we need. Okay, so that was 4. Point 5 here says change variables to generalized coordinates. Well, we don't have to do that because we actually used the generalized coordinates to begin with. And then we apply the constraints. Right. So let me move these a little bit to give some space. That's an advantage of doing this in a computer. You can move your text around. So the kinetic energy now, well, if y dot is minus x dot, that means that y dot squared is x dot squared, right? So this just becomes equal to 1/2 m1 plus m2 times x dot squared. And we're going to eliminate x from, or y from here. That's what we decided to do. So we have m1 gx. Okay, y is minus x. So just put that in there. m2g minus x plus c, which we will rewrite as g times m1 minus m2 times x plus c prime. C prime is m2gc, but as you know, a constant added to a potential doesn't mean anything, so we can just ignore this. Okay. All right, constraints applied. Next we have to write down the Lagrange equation, and for that, of course, the first thing we need is the Lagrangian itself. So the Lagrangian is t minus u. So in other words, that's 1/2 m1 plus m2 x dot squared, and then we have to add in minus the potential. And that minus sign is very important. Make sure you get that right. So that's a Lagrangian. We now need to do this for the remaining coordinates. Well, only one remains. That's x. And that makes sense if you look at the problem, right? There's only really 1 degree of freedom here. If this mass moves down, this one moves up by the same amount. So we only have one kinetic variable. And we have the same number of generalized coordinates, so that means that the system is holonomic. Okay, so now we apply the Lagrange equation. Okay, this is not so hard. On this side we get the derivative of this. So we get really g times m2 minus m1. I've incorporated this minus sign here by flipping m1 and m2. And here we get now ddt times m1 plus m2 times x dot. So that's m1 plus m2 x double dot. And then we can put this on a more standard form. We get that x double dot equals g times m2 minus m1 divided by m1 plus m2. Okay. And as usual, we should do a little bit of a sanity check. Now, we've seen this solution before, so it makes sense. But we can see here that, for instance, if we set m1 equals to 0, that gives us that x double dot equals g. And that's actually incorrect. Right? If m1 is 0, then this should move upwards. So there's a sign missing somewhere. So let's see if we can find that. Well, we'll see it up here, right? Here's positive m2, where we get negative m2 there. So there's a minus sign there, which means we get a plus sign here. And that means in turn we have to flip m1 and m2 over here and here. Okay, so now if m1 equals 0, then x double dot is minus g. And that makes sense. If we set m2 equals to 0, we get that x double dot equals g, which also makes sense. And if we set that m1 equals m2, then we get that g equals 0, which makes sense because then everything is in balance and there should be no acceleration. All right, so this checks out. So, as you can see, this is probably a little more complicated than solving the corresponding problem using just Newton's second law on the F equals ma form, but not by much. And when we get to more complicated problems, there's definitely an advantage of going this route. So we'll solve one more problem in this video that is perhaps a little more complicated and one that you haven't seen before. So this is the case of a particle attached to a spring and confined to a cylinder. Okay, so what I mean by that is this type of geometry. We have a cylinder here of a fixed radius r. Put it over on this side. And there is a mass here that can only move on the outside surface of the cylinder, and it's attached now to the center of the cylinder here through this spring here. Okay, so it has spring constant K. All right, and let me bring up the rules here for solving this. They take up a little bit more space here, so I'm going to have to do this. We'll see if I can keep everything on the screen at the same time. All right, so let's see now what we can do. We have to first ensure that the non-constrained forces have a potential. I'm going to ignore gravity here, otherwise that is of course also has a potential, but just to make things simple, the only potential I'm going to consider here is the spring potential. So we have an elastic potential. Okay, generalized coordinates. Well, we're working on a cylinder, so I think it's probably a good idea to choose cylindrical coordinates. And then we should write down the potential and kinetic energies in the inertial coordinates. So let's first ask, are the cylindrical coordinates inertial? Yes, they are. Okay. So let's begin then with the kinetic energy. So in kinetic energy in cylindrical coordinates here, we have 1/2 m. We have the velocity in the rho direction squared plus the velocity in the phi direction squared and the velocity in the z direction squared. Okay, so that's 1/2 m. Well, in the rho direction it's simple, it's rho dot squared. Now in the phi direction, you should know that that is rho phi dot. And you should be able to justify it to yourself geometrically. Don't memorize it, just understand why that's the case. That's the way to go. And then we have z dot squared. Okay, so that's the kinetic energy. Potential energy. Well, we have 1/2 k times r squared. R is the distance to the center here. We've taken the origin to be the location where the spring is attached. Now we're not working in spherical coordinates, so r is not one of the things we're going to work with. But we do know that just by Pythagoras' theorem, we can see that we have z here and we have rho there. So r squared is z squared plus rho squared. So this is 1/2 of rho squared plus z squared. Okay, so that's the kinetic and the potential energy. Constraints. Well, the constraint is that the mass can only move on the cylinder. So that means specifically that this variable rho here has to be equal to r. So rho equals to r, and rho dot equals 0 because r is a constant. Okay, change variables, doesn't apply. Apply the constraints. 1/2 m r squared phi dot squared plus z dot squared for the kinetic energy, and for the potential energy, I forgot a k over here. We get k over 2 z squared plus a constant, which is k capital R squared over 2. But constants don't matter when it comes to potentials. All right, the time has come to write down the Lagrange equations. So we need to know what the Lagrangian is. Okay, for the remaining coordinates, we should write down the Lagrange equation. Well, we started out with rho, phi, and z, but rho is no longer a coordinate because of the constraint, so we just left with phi and z. So let's work first with z. Okay, so we have the Lagrange equation in the z direction. That becomes the L dz equals d dt acting on partial dl dz dot. Okay, let's look at this. Well, here we just get minus kz. On this side becomes mz dot there, so that is mz double dot. In other words, we have z double dot equals minus k over m times z. This one you should recognize as the equation for the harmonic oscillator. So in the z direction, we have harmonic motion with the frequency omega equals the square root of k over m. All right. So that's the solution in the z direction. Now let's look at the phi direction. Well, the potential doesn't actually depend on phi, so we just get 0 equals mr phi double dot, which we could write, if we like, as mr phi dot equals a constant. Now let's see here. There's actually a problem. You can see that here because the unit isn't right. Every term here is supposed to have the unit of energy. So mass times velocity squared, that's the unit of energy. Here is mass times velocity. So we have 2 times here, meters per second squared, but it should be meters squared per second squared, so there's something wrong there. So we see we've actually forgot the square over there. So it's mr squared times phi dot squared. Okay. So that's what we get there. So mr squared, that's the angular velocity. That's I. Phi dot is the same thing as omega, the angular velocity. So I is the moment of inertia. So you get I times omega. Mr squared is the moment of inertia. Phi dot is the angular velocity. I times omega, that's the angular momentum L, and that's supposed to be a constant. Over here we can say this is equivalent to saying that L dot is 0. So we have conservation of angular momentum. So all that's going to happen here is that we have a constant omega. That is, we have constant motion in a circle around this cylinder. Not in a circle, but constant motion around the cylinder where the angular velocity is constant. And that comes, of course, from that equation. So that's a solution. Harmonic motion in z, constant angular velocity around the z-axis, around the circumference of the cylinder. So these are 2 simple examples of using Lagrangian mechanics to solve mechanics problems. The next 2 videos, we're going to solve a couple that are a little bit more complicated.